Hi class, we are on to section 8.2. Today we're going to talk about the graphs of polar equations. So in the last section we talked about going back and forth between rectangular and polar coordinates. So today we're going to look at what the graphs of polar coordinates typically look like, polar equations. So in order to graph polar equations, we really just kind of go through the unit circle. We just look at one value of an angle at a time. Now that could take very long, so typically what we do is we go through the standard angles that we use on the unit circle, right? The pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, etc., right? So when we look at these equations, remember r is my dependent variable. It's always on the outside. And then we have some function of theta on the other side of the equal sign, okay? The easiest way, really the only way to kind of graph these until we get our bearing straight, is to look at these one value of theta at a time. Even after that, it's really hard to graph polar equations unless they have very, very specific forms. And you can say, oh, this is this kind of an equation, this is this kind of equation, the graph looks like this, the graph looks like that, right? So we really want to look for symmetry if we can. So we'll talk about that in this video as well. If we can determine the type of symmetry, then that will limit us to only looking at a certain range of values for our angles, okay? So for instance, if I know that I have symmetry across the y-axis, which we're not going to call the y-axis anymore, then I don't have to look at everything from 0 to 360 degrees. I can just go from 0 to 90 degrees. And then maybe look at the bottom half of that, go from 270 degrees to 360 degrees. And then I know that that just mirrors itself across the axis, right? So if I know the symmetry, it limits the amount of work that I have to do, okay? So let's look at some examples. So let's graph r equals 3 cosine 2 theta, okay? So if I make a table of values, this is the table of values that I would get out. Now, normally, I would go one at a time. We don't need to do that because there's a lot of angles. So if you notice, I go from 0 to 2 pi. I go through the standard range of values. And as I do so, I'm plotting my outputs, right? If I plug in 0, cosine is 1. That gives me 3, right? Pi over 6, that's going to give me my 1/2. So then I'm going to get 3 1/2s, right? And so forth down the line. And if you notice, a lot of these values repeat. 3 3/2, 0, negative 3/2, 3, negative 3. It's the same thing over and over again, okay? Because it's a cosine, right? So if I start to plot these values, this is the graph that I would get. This four-leaf clover shape, okay? And so even plotting, let's just say the first quadrant, okay? So if I knew that this had symmetry across the different axes, I would really just have to plot the first quadrant, and then I would notice that it flips and it repeats itself. But notice even just the first quadrant values, right? So 0, pi over 6, pi over 4, pi over 3, pi over 2, these ones. If I plot just these 5 values, there's no way I would have really known that it actually looks like this, right? I really have to plot a lot of values in order to really understand what this curve looks like, right? So at the first one, I would have plotted 3. The next one, at pi over 6, I would have plotted 3/2. So I would have went to 1.5, and then I would have found my angle. But how would I make sure that this is what happens in between those two values here, right? Unless I plot even more values. So typically when we graph polar equations, we typically want to use a grapher for these. It's very hard to really figure out what's happening in between any two values. And then we also have to plot these in polar coordinates. So if you notice, just looking at this, if I wanted to plot this point, I kind of have to say, okay, well, the radius is 3/2. I go up pi over 6. Where does that land on my Cartesian graph, my rectangular coordinate system? It's kind of hard because I have to do a lot of conversions, right? From into polar coordinates, from the polar coordinates into my rectangular coordinates. So we have a polar graph, right? Which is a lot easier to plot polar equations on, okay? So again, polar coordinates generally, as you see, are some sort of curve, okay? They're very, very much so related to circles, as we said before, because we're talking about radii and angles. So when we talk about a polar graph, we have different axes, okay? The origin from rectangular coordinates we call the pole in polar coordinates, right? Because everything centers around that pole. The polar axis is the same as the x-axis, okay? So instead of calling it the x-axis, we're calling it the polar axis because there is no x in polar coordinates, okay? So that's our polar axes. And then what happens is we put, instead of plotting squares at distance of 1, 2, and 3, we plot circles with radii of 1, 2, and 3. Okay, so it looks like this. This is the graph that we would use for polar coordinates. It generally goes up by tick marks of pi over 12, right? We generally count by pi over 12s. Although, you know, you can stick with the ones that we know. The thing is, if we say with pi over 6 and pi over 4 and pi over 3, that leaves this gap here, and it leaves the gap here. So we generally count by pi over 12s. Notice again, as I said, these circles vary by radii of 1, 2, 3, 4, etc. Okay, so if you can see, I have the first quadrant, right, equivalent here, then the pi and 3 pi over 2, and then back to 0. Again, this is the pole, this is the polar axis. Okay, so it's a lot easier now, because if I want to plot something like 3/2 pi over 6, right, I know that my radii is 1.5, so here, and then I go up to pi over 6. Way easier to plot that point here than it is to come here and say, okay, I know where 1.5 is, but how far up exactly do I have to go for pi over 6? Okay, where exactly does that lie on this XY coordinate system? And it's probably got some crazy long decimal form approximation for that exact point. So that's not very fun. This makes it a lot easier to graph our points. Okay, so let's talk about symmetry. Okay, if I plug in negative theta into my equation and I get out my original equation, then I'm going to have symmetry across the polar axes, right? So that would be the same as symmetry across the x-axis in that case. Okay, and an example of that would be this. So notice that across the center line, right, the horizontal center line, what I have on top is mirrored on bottom. Okay, so again, if I plug in negative theta into my equation and I come out with the exact same equation, I have symmetry across the polar axis, the y-axis. Okay. If I plug in, if I take my function and I change all of the signs in it and I get the exact same equation out, then I'm going to have symmetry across the pole. Okay, this is symmetry. This is similar to symmetry across the origin in our regular XY coordinate system. Okay, so another way of working with that is if I add pi to my angle, then I get the same thing out. So these two statements are equivalent. Okay, if that's true, then it's the same thing as if I flip it across the polar axis and across the vertical axis, right? So that's the symmetry that I observe if this is true or this is true. Okay. For 3, if I plug in a negative pi, okay, instead of positive pi, and I get out the exact same function, then I'm symmetric across the horizontal axis, or the line theta equals pi over 2. Okay, what would have been the x-axis. So it's the same thing as we had before, where we had symmetry across an x-axis, a y-axis, and an origin. It's just that now that we're in polar coordinates, we have to look at it a little bit differently, right? Plugging in a negative angle, or changing the sign across my entire function, or equivalently adding pi to my angle and getting out the same function, or subtracting pi from all the angles. Do I get out the same function? Okay, so here you can see symmetry across the vertical axis here, right? So we always want to test for symmetry. That would be one of the first things that we want to do, because if we know the symmetry, as we said before, I wouldn't have had to look at every single angle here. I could have restricted myself to just going, okay, 0 through pi over 2. What does that quadrant look like? And then it doesn't matter how I flip it, because this has symmetry across the origin, across the polar axis, and across the line pi over 2. Okay. All right. So let's just look at some common polar curves. Okay. So the first one is a circle. If my polar equation is r equals a constant, well, that means that I have a circle with a radius of whatever that constant is, right? If the polar equation is r equals 2, that's a circle with radius 2, right? It's saying that my radius is always equal to 2. Okay, so remember, we're talking about circles here, right? Sines and cosines. If I have r equals a sine theta, well, that's basically looking at always having a radius of a y value, basically, at that point, right? Some multiple of a y value. So it's not necessarily a circle, but it is a curve over that's always positive, right? Positive y values, positive values here. We can make this a circle depending on how we adjust the value of a here, or if we multiply something times this theta here. In this case, actually, it is a circle, so that's nice. Here we can move the circle to be on positive values of what would be x in rectangular coordinate systems, right? So it's really just shifting our circle around the pole at that point. Okay. And if we have r is a times whatever angle we're looking at, well, the radius is growing depending on a growing angle, right? So that's going to give us a spiral. Okay, so these are the most common things for us to look at here. Okay. So we have what are called limicons, which have the form a plus or minus b cosine theta, or a plus or minus b sine theta. Okay, depending on what we're using, cosine or sine, and depending on the values of a and b, will vary the orientation of our limicons. So here, if a is less than b, we get this kind of curve. So here, notice we're located only on the positive portion of what would be x, so this has a cosine, right? There's no sine here. This would be a plus b cosine, because it's on the positive part of the cosine. If we had a negative b here, it would be on the negative part of what would be the x's. Okay, here it should be very clear that this is for sine, okay, because it's on the upper part. If it was a negative sign, it would be on the lower part. And then here, so the difference between the a's and the b's, if a is less than b, we get this internal spiral. If a is larger than b, there is no internal spiral. Okay, and if a equals b, we get a nice picture like this. So again, this would be a cosine because of its orientation, right? So I mixed it up based on cosine and sine, so you can tell the difference. So again, that's just kind of a variation of these two graphs here. But now we have something plus this or something plus that. So the orientation is the same, right? But then the a and the b values adjust what's happening with the spiral. Okay, and then we have what are called roses. So they have the form of a equals a sine some multiple of theta, or cosine times some multiple of theta, or with an input of a multiple of theta. N is the number of leaves, right? So if n is odd, then there's n leaves. If n is even, then there's 2 times n leaves. So for instance, sine 3 theta, n is odd in that case, so there's n leaves, there's 3. Okay. Here we have cosine, so you see how it's been adjusted just a little bit. There's a slight orientation to it as far as like how it's situated. So it's the same number of leaves, but you can tell that it's rotated in some form, right? Here, this is 4, so it's cosine. Since it's an even number, there's 8 leaves. Okay. I don't know why this says 4 times theta, but it's the same thing. So this is a 4-leafed, but you can see here that as well, it just has a rotation to it. Okay. Then we have lemniscates. So these are figure 8 shaped curves. So they have the form of a squared sine squared 2 theta will look like this. Okay. If I have a squared cosine squared theta with 2 theta, then it turns it into standard infinity figure 8 symbol. Okay. And those are our common graphs for polar coordinates.